My name is Katusiime Conrad, and I'm going to be discussing the work that we are required to do in data communication. Um, I'm starting with an introduction, and then the explanation follows. Multiplexing is generally the idea that we want to send multiple signals over a single channel at the same time. It is important for maximizing the efficiency and the utilization of bandwidth of a given channel. For example, the optical fiber cable. It has a very big bandwidth, but then sending a single signal over it would be wasteful because the single signal would not be enough to cover the entire bandwidth of the cable. Frequency division multiplexing is an analog multiplexing technique where we have signals modulating different carrier frequencies and then having these signals combined together but separated by different bands of other unused frequencies in order to prevent interference, and then have all these sent via a given common medium, maybe usually, for example, like air. Frequencies and the very high ones that are used for sonar and then the radio signals and satellite transmission, they all have different bandwidths, and those bands that they are assigned to, for example, from 3 gigahertz to 30 gigahertz, that is for satellite, it is separated from the one below, and there is a space of frequencies they don't use so that they prevent interference. Wavelength division multiplexing. In this one, we want to the concept is using light. Light, for example, when light is passing through a medium, when it is traveling from one medium to another of different optical densities, it can be bent. And this bending, if you have signals that have different frequencies, different speeds, because the refractive index depends on speed. So if you have components of light that have different speeds, they can be split or combined using a prism. So in wavelength division multiplexing, the technique is splitting or combining these bands of light together so that they can be sent over a given medium. On one side, the medium is usually optical fiber. On one side, you have the light being combined, and then on the other side, you have the light being separated. Both sides can use a prism. Then in synchronous time division multiplexing, this is a digital multiplexing technique. Unlike wavelength division and frequency division multiplexing, it involves sharing time slots among the channels that are sending data over a given medium. Each channel is assigned a time slot, and whether it has data or not, it's still given a time slot to send data over a given medium. The data that is collected from all the channels is combined into a frame, and it is the frame that is sent. Then interleaving comes in that we want to select the channel to send the data, but then also at the receiving side, we want to have the same channel that is intended to receive the data. So what interleaving does is we assume we have it helps in synchronizing such that when you have a frame coming from one side, the channel being assigned the time slot, as it is sending the other side, we have the same synchronization such that the channel that is receiving the communication is the actual channel that it's supposed to be receiving. Then that's for multiplexing. Now multiplexing mainly deals with the efficiency. On the other hand, we have what we call the spread spectrum. This involves spreading the bandwidth of a signal over a larger bandwidth so that we introduce what we call redundancy in order to prevent jamming and interference and eavesdropping mostly. So what frequency hope spread spectrum involves is that we have a range of frequencies that we use to modulate. We we have as we have a range of frequencies, finite frequencies that a signal modulates, and each time the signal at modulates a different frequency at any given interval. So for example, you could have a signal modulating a frequency between 100, maybe a frequency of 100. The next time, because we are hoping, would go maybe like to 300 and then 800 and then come back like to 200. Yes, this irregular pattern makes it hard for someone trying to jam the signal. If they are trying to jam a narrow signal, it will be hard because the signal is spread over wider bandwidth, and if someone was trying to interfere with the communication, they would only be able to interfere with it if they know what the next hope of the next frequencies will be. Then at the receiver side, you have a mechanism that has the same hopping frequency or knows the pattern of the frequency hopping so that they can be able to receive the data. As discussed earlier, we saw that in frequency division multiplexing, we are trying to combine frequencies, divide up a given bandwidth, and combine these into one signal that can be sent over a given channel. Now, the idea of orthogonal frequency division multiplexing is that instead of having one big band that you're modulating, you split the wide band into narrower bands, and these use a lower signal rate, thus increasing the integrity of the system. The advantage of orthogonal frequency division multiplexing is that it is able to cope with severe conditions within the transmission medium, such as attenuation and those errors caused due to multipath. When we are sending signals, for example, let's say via Wi-Fi, we can have the signal traveling to the destination but being reflected along different elements within the environment. The signals on reaching the destination may arrive longer and may blur, which becomes harder for the receiver to distinguish between the start and the end. Now, this signal element that has been blurred affects all the incoming symbols, and this is what we call the intersymbol interference. While trying to convert an analog signal into a digital signal, there are two methods that can be used. We have the delta modulation and the pulse code modulation. Under pulse code modulation, we sample the analog signal, we quantize the samples that we have obtained, and then encode. The samples that are obtained, while trying to quantize them, we can use two methods. We can quantize uniformly or non-uniformly. When we use uniform quantization, we divide the amplitude of the signal into equal intervals. This may not clearly, this treats the entire amplitude or the entire analog signal as a constant one, though the changes in amplitude mainly occur in they occur more frequently in lower amplitude. So using non-uniform quantization, it's easier to pick out these changes in amplitude that occur in low amplitudes rather than and then have those use a smaller interval at lower amplitudes and then use a higher interval at higher amplitudes so that we get the changes in the lower amplitudes. A satellite is an object that orbits another bigger object. For example, the Earth is a satellite because it orbits the Sun. And in the same way, we have the moon orbiting the Earth. So the moon is a satellite. Um, there are mainly two kinds of satellites. We have the natural ones and then the artificial ones. And in data communication, we mostly rely on the artificial satellites. These ones can have equipment that can relay information, generate signals, so they are much better and can be placed in specific orbits depending on the need. There are mainly three kinds of artificial satellites that are used, and these are the geostationary Earth orbit satellites. We have the middle Earth orbit satellites and then the low Earth orbit satellites. The geostationary Earth orbits, these have the same period as the Earth, and to someone on the ground would appear stationary. The thing about them is that they require a line of sight, so they are only connected to one point on the ground, and you would require, because if they appear stationary, you would require three to cover the entire Earth. Their main orbit is the around the equator, the equatorial orbit. We have the second type, the middle Earth orbit satellites. These these are located between the two Van Allen belts, and that is somewhere below the geostationary Earth satellites. The middle Earth orbit satellites are mainly used for GPS and navigation. Then the third type, we have the low Earth orbit satellites. These are closer to the Earth and are located below the lower Van Allen belt. These satellites, for example, including the International Space Station, yes, are used for communication on Earth because they are much more nearer, and the transmission between them and between the ground and them is much faster. These are mainly used for telecommunication, sending signals and radio frequencies. Yes, and those are the kinds of satellites that we have.